Today, we're going to take it quite easy. I also have to take it a little easy, because my voice may be petering out if I'm not careful. We're going to apply today what we have learned. So there's nothing new, but it's applications. And that's important, things that you can let it sink in. We have here a trajectory of a golf ball or a tennis ball in 26/100. We shoot it up at an angle alpha. The horizontal component in the x direction is V0 cosine alpha, and the vertical component is V0 sine alpha. It reaches the highest point at P, and it returns to the ground at point S. This is the increasing y direction, and this is the increasing x direction. We're going to use very heavily the equations that you see here that are so familiar with us. These are the one-dimensional equations in x direction where there's no acceleration, and the one-dimensional equations in the y direction where there is acceleration. In order to use these equations, we need all these constants x0, v0x, and v0y. We have seen those last time. I choose for x0, I choose 0 arbitrarily, also for y0. The velocity in the x direction will never change. This v0x will always remain v0 cosine alpha. The velocity in the y direction, however, in the beginning at t equals 0 is v0 sine alpha, and that one will change because there is here this t, and that's why the velocity is going to change. This t will do it. And the acceleration in the y direction, since this is increasing value of y, is going to be negative 9.8. Since I call always 9.8 plus, since I always call g plus 9.8, this is minus g. I now want to ask first the question that you may never have seen answered: what is the shape of this? Well, we can go to equation number 3 there, and we can write down, this is equation number 3, that y as a function of time equals v0 yt, so that is v0 sine alpha times t minus 1/2 gt squared. That's the equation in y. I go to equation number 1, and I write down x at any moment in time equals v0x times t, so that is v0 cosine alpha times t. Now I eliminate t, and the best way to do that is to do it here, to write for t x divided by v0 cosine alpha. Now I can drop all sub-indexes t, because we're now going to see x versus y. We're going to eliminate t. So this time here, I'm going to substitute in here and in there, and so I'm going to get y equals. There's a v0 here, and there's a v0 there. That cancels. There's a sine alpha here, and a cosine alpha there. That makes it the tangent of alpha. And then I have here an x. Then I get minus 1/2 g times this squared, x squared divided by v0 cosine alpha squared. And now look very carefully. Y is a constant times x minus another constant times x squared. That is a parabola. It's a second order equation in x, and it's a parabola, and the parabola has this shape. So you see now, by eliminating the time, that we have here a parabola. Now I want to massage this quite a bit further today. I would like to know at what time the object here comes to a halt, to its highest point. It comes to a halt in the y direction, it comes to a highest point, and I want to know how high that is. Well, the best way to do is to go to equation 4 and to say to equation 4, when are you 0? Because that is the moment that the velocity in the y direction becomes 0. It must be at its highest point then. So in order to find for us the position of the highest point P, we first ask ourselves the question from equation number 4, when is the velocity in the y direction 0? And that then becomes v0y, which is v0 sine alpha, minus gt, and out pops that t at point P is going to be v0 sine alpha divided by g. So that's the time that it takes for the object to reach the highest point. Where is it then? What is the highest point above the ground? Well, now you have to go to equation number 3, and you have to substitute this time in there. So that highest point h, which is y at the time t of p, equals v0 yt, that is v0 times the sine of alpha, but I have to multiply it by this time. And so I get another v0 sine alpha, and I get a g here, minus gt. This equation, minus half gt squared, minus 1/2 g times this one squared, which is v0 sine alpha squared divided by g. Divided by g squared. Because there's a g here, you see. So you square the whole thing, it is t squared. You lose 1g, and you will find then that the highest point, let's write it down here so that we don't block that blackboard. The highest point in the sky equals v0 sine alpha squared divided by 2g. That is the highest point. Let's give that some color because we may want to keep that. Is it reasonable that that point, that highest point in the sky, gets higher when v0 is higher? Of course. If I shoot it up at a higher speed, of course it will get higher. So it's completely intuitive that v0 is upstairs. If I increase the angle from a small angle to larger and larger and larger, is it reasonable that it will get higher? Of course. You all feel in your stomach that the highest possible value you can get is when you make alpha 90 degrees for a given velocity. That's the highest it will go in the sky. So clearly this is also very pleasing. If you did the experiment on the moon, with the same initial speed, it will go much higher. So you're also happy to see that this g here is downstairs. So that makes sense. At what time will the object be at point S? Now there are two ways that you can do that. You either go to this equation, number 3, and you ask equation number 3, when are you 0? And it will give you two answers. It will say, I'm 0 here at this time, and I'm 0 at that time, and those are the two times that you want, and this is the one you pick. That's perfectly fine. I think there's a faster way to do it, and that's the following. This is a parabola, so it's completely symmetric about the vertical about P. So to climb up from O to P must take the same amount of time as to go down from P to S, and so I claim that the time to reach point S must be twice the time to reach point P, and therefore it's going to be 2v0 sine alpha divided by g. But now we want to look again whether the v0s and the sine alphas have the right place. Indeed, if I increase the speed, I would expect it to take longer before it reaches